Hello, hi everyone. Today we'll be talking about searching problem, particularly uniform search. So let's go back to whatever we discussed in last week, the data about what is the state. So whatever the information you will have about the environment, what is the environment? You can think it as the real world. Whatever where the problem setting will be specified, this you consider as the environment. All the information about the world given is state information for you. Those information required to make appropriate decision is known as the state. For example, I'm giving you lecture, right? So my state is whatever I have learned till today. So someone will ask me, I'll reply that, right? So in order to reply, I need to have some background and whatever study I have done. So this is known as a kind of state, where in what state I am, and the action would be to reply to the question whoever will ask, right? So I remember Professor Mawsam said in one of his talks that any problem can be treated, as a search problem. So when you go for a AI model, the simplest thing you think about that, what is the input and output, right? That will make things very clear to you when someone is explaining something to you and you don't get it. Just ask what is the input to the system and what is the output. Fine, what model is doing, model is transforming input to output. That's what it is doing, right? So this is very important analogy to take up while discussing some AI problems. So you think about input, output, and how input is being transformed to output is our AI system, right? So search strategy. In one of his talk, he also said you give him any problem and he'll convert into kind of search problem. That's true. I also believe to this, because what is happening, whether it's a classification generation task, you are giving state information to a model. Finally, model is mapping it to some hidden space, and that hidden space maps it to some outcome space. So ultimately it's searching appropriate space for a given state. That's what all happens, right? A search strategy is defined by picking up the order of node expansion. Now we'll mainly talk about how to do searching. So searching is visiting different nodes of a graph, tree, or a structure. So we'll be talking about that. So in what terms we'll compare to algorithm is the completeness, time complexity, space complexity, optimality, and systematicity. So these are the 5 components on which we'll judge. Completeness means, does it always find a solution if one exists? This is known as a completeness. So there might be some algorithm where you will run, but still it will not go to the solution. So this problem may occur there. Time complexity, how much time it is taking to run the algorithm. Space complexity, how much computer space it is occupying. Optimality, does it always find a least cost solution? Yeah, so this is something tricky. What is optimality means? Optimality, fine, it is finding every time some solution given a scenario, but does it the optimal path? Is it the optimal path? If it is, some cost is associated with each transition from one node to another, does it taking the optimal path? This is the meaning of this parameter. Systematicity, does it visit each state at most once? So is it also visiting one node more than one times or not? So if it is visiting each node at most once, it is known as a systematicity, right? Now 3 symbols that we'll be using throughout the lecture is are B, D, and M. So what is B, D, and M? Let's understand about that. So B is the maximum branching factor of search tree. So branching, given a node, how much branch it has. So this is the give you the sense of the branching. D is the depth of least cost. How much depth it can we have of the tree is the D for that. Maximum depth of a state space may be known as M. So M is a kind of symbol they have given. Maximum depth of state space, how much space it can have. Now coming to few search problems. What are the search problems? I might have seen this picture, which is 8 puzzle problems. So there is a blank box, and finally you have to sift that blank box and go from one state to another state. For example, this is a start state and this is a goal state. How will you go there? So you can see here there can be four possibility. One would be go up, down, left and right. So taking one operation at a time, going to another state and then from one to another and like that until you reach the goal state. So this is a kind of searching problem because you are modifying the state each time, right? And finally checking whether it has reached goal or not. If not, then you are going further search, and then there are four terms: states, actions, goal and path. Goal state, you can see whatever the where you want to go. Start state is the initial state where you are is, and from initial state to goal state, whatever the state transition you will do are the different states. But this is not the only stage, it can also have the other state as well. So whatever the possible combination of start state you could do given the constraint is are the states, right? What are the path cost? Path cost means doing an operation, how much does it cost? For example, this is a blank box, right? So the cost might be for going up would be 2 unit, let's say, and for down it's a 1 unit. For left and right it's 1 unit. So always better to go down rather than up if both are leading to same kind of scenario from where the reaching to goal would be similar of complexity. It's quite similar to analogy. If it's say taking up stairs, going up is more difficult compared to going down. So this is one example. If you see, this is the source and this is the target. One blank, this blank is known as a blank 2 4 3 4 5 6 7 8 and 1 2 5 3 4 blank 6 7 8. So saying this is the source and I need to go to target, how will you go that? You have a 3 options. If you see for this blank, you cannot go up, right? Because there is no such way. You can go down, you can go left and right. So from here to, if I have to go to target, what should I do? Should I go down or should I go left or right? What should be the optimal thing that can be done? So for example, if you see this scenario, what could be done? Going right seems more appropriate. So if you go to the right, it will be 1 2 blank, right? And then whatever the situation you have. Now from that state 1 2 blank, if you just go the blank to down, it will be 1 2 5 blank, and everything is matching as target finally. So in 2 states you are going to the target. So this is how operation works. That's why I wanted to show. Now coming to the example, this is the formal definition of states. Location of the tiles. Whatever the location of the tiles you have in this given scenario are states. States actions are move blank left, right, up and down. So there is a blank path, right, that you can either up, down, left and right. Goal test equals to goal state. Whatever the goal state you will be given to reach. Path cost 1 per move. For example, it is defined here, but in various problem given the action cost also differs. So that's why I said going up would be 2 compared to going down, which will be 1. Note, optimal solution of n puzzle family is the NP. Yeah, this is the very important point you need to see, is the optimal solution for n puzzle problem is the NP hard problem. So this is one example the professor has shown in his lecture. This was the current state 1 2 3 8 blank 4 7 6 and 5. So from here what you can do, blank has the 4 options. It can go left, right, up and down. So if first this has gone up, this one has gone right, this one has gone down and this one has gone right. So this is the 4 possibility. From here you have how many possibility? You have again 2 possibility, right? Shift the blank to left and right. That's what it has been done. For this one also it has the 2 options to either go, for this is the blank. So what you could do, you can do blank to up and down. So there are the 2 possible. Similarly for other also it has been expanded. finally the expansion goes on. So you have to go do the expansion until you reach to the goal state, and from there onwards you can do any searching algorithm, which could be either, let's say you are doing BFS, then you should do the breadth first, this, and in depth first what you do, you go deep. So you take this one, then this one, then this one, and then go deep about that, right? Another important search problem is the n-queen problem. So you might have played, chase game. So it's same as that. So a blank chase I'll give you 8 queens. I'll say arrange them in such a way so that no two queens attack each other. This is the problem statement that has to be solved in n-queen problem. So what are the states? States are the any arrangement of 0 to 8 queens on the board is a state, right? Which is the initial state, no queens on the board, everything is blank. This is the initial state. Actions, what you have. So there are how many actions? Add a queen to any empty square. So you have some options, right? What are the actions? Add a queen to any empty square. So I have 8 queens. When I'm starting, I can put queen to the any place because everything is black. When I'll put another queen, I'll make sure that it should not contradict with the first queen. When I'll put the third queen, I'll put it in such a way that it should not, again contradict to other 2 queens. Goal state is 8 queens are on the board and none attacked. So this is the final scenario what we are expecting. Now coming to uniform search. So what is uniform search? Uniform search is like you don't have any information. You have the equal information about the nodes and they are equally likely. This is the data you have given, and you have to do the search strategy. But in life we don't do ununiform search. We have some data about the problem we are doing, and then we try to use those heuristics. But here no such heuristics are given. Uniform search strategy is only the information available in the problem definition itself. No additional information will be given. So there are 4 most popular uniform search strategies: breadth first search known as BFS, depth first search known as DFS, and depth limited search, iterative deepening search are 2 another search strategy, uniform search strategy. Now we'll talk about the BFS. So this is, let's say, scenario given to you. A is the root node, B and C are the child. For B, there are again 2 childs, D and E. For C, there are 3 childs, F, G and H. So we need to use some data structure to visiting the nodes. Can anyone say why Q is the most appropriate here? Or Q is not appropriate? Should you use some other data structure such as stack or something else linked in? So in BFS, what we say is, you are visiting one node, you see all the association of that node first. This is the BFS. So here you are at A, you see all the association B and C. Then you are at B, then you see all the association D and E. This is the breadth first search. But if you are using here depth first search, you are seeing A, it's saying okay, go for B, another node, go in depth again, D, not E. For D, you see if there is any child, then you go there. Is it complete algorithm? Yes, it is. What is the time complexity? Time complexity B ki power D, right? So those things we discussed there. So what is B? What is D? B is the depth. B is the branching factor, and D is the optimal depth, right? So these points you need to keep it. Maximum branching factor of search tree is the B. D is the depth of least cost solution. So there would be solution, right? So what would be the depth of that solution is the D representative. M is the maximum depth. So this is the difference between M and D. So its time complexity is order of b ki power d, and the space complexity is also similar. Why it is so? So for example, if you see b is the branching factor and d is the depth, so what we do in the breadth first search is like we expand breadth first. So if your, let's assume your solution as a depth, it has to go till the b, all the b solution it has, b children it has to see. So that's why it is O ki power b of t. Now depth first search, by name it suggests its property is to go depth first, right? So rather than going here and then, if you has expanded one node, what is the children of that node you have to see and go in like that. So maintain a stack of nodes to visit there. So this is the reason why I ask you what is the most appropriate data structure about that. So we'll discuss why stack in queue, but before that let's understand the DFS in detail. So DFS says you need to go in D first. So for example, if you are at the A, if you have expanded C, it is saying you don't see other nodes, you should not see this blank one, you go depth for that. So for C, it is again saying don't see any blank, you go in depth, so G and then the depth of G and like that. So this is what the depth first search, how it works, right? So if you see depth first search, we are going deep. So if you are putting all the nodes, you just have to do what. So for example, A, then C, then G, that's where we are doing. But if it is a breadth first search, we are doing A, B, C, D, E and like that. So this is the difference between breadth first search and depth first search. So for depth first search, most appropriate data structure is a stack, right? While for the queue it is, for the BFS it is queue, because here you are doing this kind of traversal is the reason why we are taking queue here, but in DFS we are taking stack. So I don't know whether you all be remembering those property or not. So there are properties of this data structure, LIFO and FIFO, last in first out and last in first out and first in first out. First in first out means those who come first will popped out first, but for LIFO, last in first out, whoever will come last at in the list will be popped first. And that is the reason why they are applicable different for these different algorithms. Now next question is it complete? Depth first search is complete. Complete means, is it finding every time solution? No, it doesn't. So that what is the time complexity? Time complexity is b ki power m. B is branching factor and m is the maximum depth. Space complexity is bm. Now come to the another kind of solution, which is cheapest first. So it says if I'll also give A's weight in each, two nodes are connected by A's, fine. If you'll also associate some weights to each A's, and the strategy is that you do cheapest first, right? So for example, this given scenario, what you will choose, whether for A you will choose B or C, you need to do cheapest first, so you need to go for 1. So this is the how it works. So you reach to B. From B, which one you will choose, whether D or E? You will choose D because you are doing the cheapest first, and like that. But it is not same as depth first search. But for this example, it seems like similar to that. But if one and the other one would be, let's say 0.5 here, for example. Yeah, it's a special kind of deep first search. If it is depth first search, what we have done, A, B, D and like that. So here, if this number, if I have switched for A's weight for A and B is 1, if I switched A's weight between BD and BE, let's say the weight of BD is 6 and weight of BE is 2, then the expansion would something look like ABC. ABE. It would not be ABE, because for BE cost would be 2 and for BD cost would be 6. That's why we are not expanding BD first. And while in deep first search, when depth first search, we always expand BD first compared to BE. So this is the difference between the depth first search and cheapest first. Don't intermix these two algorithms. Now, what is the time complexities? It's a C is the cost, optimal cost. C by E is the is, right? Space complexity is it's B ki part, C star indicates the optimality. Is it optimal? Yes, it is, because that was the definition of optimality, right? So if it is finding solution, that's cool, but it will take the solution of those path which will cost least, or in some sense cost also defined as maximizing something, might be reward. So it should take the path which is giving you the maximum reward. So don't intermix these two words. So people might I have seen confuse a lot of times. So sometimes objective either to maximize or minimize. Maximize would be what? We need to maximize the, let's say, reward, and we need to minimize the penalty. So for example, here what we have to do, we have to cheapest first, we have to minimize the cost. But in some sense, if I call it as a reward, then it would be like, maximize reward, right? So this is the difference between objective is just a reverse of each other, maximize and minimize. But given the problem, it has to you have to expand accordingly. Now we'll go and further discuss about other algorithms and understand how things are going there. So just a second. So for algorithm, what matters? Time and space. Another name for space is memory. Now we'll think about, we have discussed many algorithms. BFS we discussed, DFS we discussed, cheapest first we'll discuss. Now in terms of time and memory, which one is the better, or something like that? Let's discuss about that. Time, depth, this is the depth and how many nodes are there. If it is 2 depth tree, then there are how many nodes? There are 110 nodes. And if it has to do which algorithm it is BFS. So for BFS, we are analyzing what? Time and memory. If depth of the tree is 2, number of nodes would be around 110, and the time it will take very less, which is 0.11 millisecond. Memory it will occupy 107 kilobyte. But if you just do the double, the depth 4 nodes expand drastically. Why so? Because the branching factor is so high here, it's a 10. So that's why it is let's make you sure why for depth 2 why number of nodes are at 110. Can anyone calculate it how it is happening, or I'll then discuss about that why it is 110. Branching factor is 10. So if you can see the relation between depth and nodes, as you increase the depth, keeping your branching factor constant, the number increases drastically. For depth 2, number of nodes 110. For 4, it's 11110, and it is going every time 10 ki power 2 if you just multiply, because branching factor is 10, and for if you are extending for the 2 depth, it will be what? It will be 10 into 10, and that's why 100, right? So every time, that's why it is being multiplied by 10 ki power 2. So this is why the reason it was. So this was not the exact number, they are just giving enough power of that 10 ki power 12 and like that. So if you can see, if branching factor is 10 and depth is 16, will take 350 years times to do BFS. 350 years, can you imagine? And will take memory up to 10 exabyte, right? Which is huge, right? So this is one, trade-off has been given to you, what you want to maximize with the time or the memory. Maximize in the sense optimize, that's what I'm saying. So this is taking 2 minutes and 103 gigabyte. So in nowadays, if you see, we are not caring much about memory because we have lot of space. No, we don't have that much space problem. We have the time problem. If some solution, if algorithm is doing the task in half time and it is taking 4 times memory, I'll be always happy with that, because the time is matter most. Why time matters most? Because it is something which you cannot get it, but the space you can reuse it, space you can merge it, and something like that. For this, you need to think about that, why it was like that. Right, now coming to the next slide, which is about the beam search. So what is the idea about the beam search? If those who are doing some research, particularly in NLG, natural language generation, they might have heard this term beam search a lot of times. So beam search says, okay, no issue, they are giving a kind of one restriction here. The restriction is that maintain a constant size frontier. Whenever the frontier becomes large, prune the worst node. So it is saying you decide some constant size frontier. Frontier means how much you are going to open with that the given expansion, right? So you fix that, and whenever it is becoming crossing the limit, you need to prune the worst node. Prune the worst node means, if you are in terms of cost, if I have to say you are expanding that, you have to prune it. Is it optimal? No, it is not, because here you don't have the completeness also. It is not complete as well. Optimal says is always find the optimal cost path. Now another searching strategy is iterative deepening search. What it says for depth first search, what you used to do. For depth search, we go A, for B, for D. We are going in depth, right? And here the how much depth you can go, it is the maximum depth that is allowed. But here you are saying, let's decide some maximum depth for, let's say 2. And in 2 you haven't reached there, you make it double it, let's say 4. And then 4, if you have not, this 8. So that way you will not expand too much of depth of the tree if it somewhere lies in the above there, but in the another side. So that time is being saved for this algorithm. So did you get the idea about the iterative deepening? If you think in a bit depth, you'll get it. Let's say I'm explaining with this example. So this is the scenario, for example, but you consider the depth of the tree is too high. So what will happen? A, B, D, and whatever it comes, it will go like that in depth, right? But solution would have been C, then something a C or F or G, then it has to come back. Let's say the depth is 1000, then it has to explode all those nodes till the 1000 depth, and then it has to come back again to A and then go to C, and then F is the solution. So this time is becoming so huge. So what it is saying, iterative deepening, it says you start with some threshold, depth would be 2. If you till 2 you haven't reached, for example A, B, D, then you backtrack and come to A, and then go then you increase your depth, double it, your depth. So from 2 we are doing it 4. So then it goes in that direction and go like that. So this is one example it has been given. Iterative deepening search, if it is 0, this is the root node. If it is deepening 1, you are expanding one node at a time in depth. Iterative deepening search equals to 2 here. So you are going to the second level. 3, you are going to the third level. So this is the efficacy of iterative deepening. Is it complete algorithm? Means if there used to be solution, will it find the solution every time? Yes, it is. Because if you see, it is quite analogous to the DFS and with some addition constant. So if there used to be solution, then why here it will not be solution? So here we'll also have some solution about that, right? So for DFS it is not complete. Sorry, I mistaken it there. So for it will not, if there will be solution, you cannot guarantee that every time you will get the solution. So but iterative deepening is complete. Every time if it used to have a solution, it will guarantee to converge there, it will guarantee to reach there. So try to understand what is the difference between these two. It's quite similar with that DFS, but that limitation has been alleviated here. So how does it happen? Just think for a second and then I'll say why it is happening. So see here that limit was 1, here 2 and 3. So in 1 we have expanded these 2, right? Iterative search is equals to 2. So what happens here, if you see the difference, we are going at the second level as well. So we started with the root, we expanded this blue one, right? Blue one in the all possible. If for 3 we are going in the 3 level. So if you could observe the scenario here, what is the difference between general DFS and here? If it would have been general DFS, we'll go depth and depth for that, but it is saying no, you don't go that depth. Given the limit, you come back and then go in the given depth, right? So that's why it is how it's different from the DFS. And in DFS that's there, but it is guaranteed to converge to some solution. What is the time complexity? Time complexity is again exponential, which is b ki power d, right? A space is also same, not same, it's a factor of these two attributes only, but not in exponential term, but multiplication, order of bd. Is it optimal? Yes, it is optimal if step cost is 1. Step cost, what does that mean? Node of each cost is 1. Not node to node, is can be modified to explode uniform search iterative lengthening. Now coming to these few problems. So let's say this was the graph. What is the BFS order? BFS order, we are starting from A, then BFS order we go for in the breadth first search. So you will go for A, all the childs of A you will explore. So A I explored, and then its child, which is B and G. So I put B and G. when the goal state was G, that's why we stopped here. If we have done here rather than BFS, we have to do, you know, DFS. What would be the solution? We have gone A to B, and then B to C, then C to D, and then D to G, and this is how the DFS works. So A, B, C, D, G. We reach to the goal state, but we have go in depth rather than in breadth. Another one is IDDFS, iterative deepening depth first search. So it's a kind of DFS, that's why we are calling it as a iterative deepening. So for iterative deepening, we initially have in one size we are going for A. For if you have make depth to be 2, then it would be A, B, and G, right? Because you increase the depth. There used to be one problem if you have to observe. If you to, it would be, you know, there would be some cycle, then there is a problem. For example, this and this, what is the difference? There used to be age you can observe now. So this is the, there used to be directed age, but here there is no direction for A to B, and B can also go to A, right? So what problem it will lead to for DFS if will do. So for A to B it will go fine. For B it can go to C and A as well, right? Because the both way possibilities. So again it will take A, because if you have restricted lexicographical order, then if from A to B it will go, it has two options, C and A, but lexicographic order if you have, it will go to A. For A it will have option to go to B and G. For lexicography it will go to B, and this loop will be there. So this is one problem also occurs if it is rather, you know, not directed graph, then this kind of things happen. What is the solution? Solution you can have, you know, mentioned here. Partial reduction in the repeated expansion can be done. So that those repetition we need to track somewhere. That, for example, this was a scenario for A to B and from B to A. Why should we go to A? That you should. How will you know if you have tracked it, if you have saved it, that you have already, you know, explored that node, then you will not go there. So this is where you can, you know, restrict that part, that wherever you have already reached, please don't go there. Now there used to be something, if you see, forward search and backward search. So this is, let's say, start state. You are from here, you are going to all where. If I say goals, let me give you an analogy for, you know, forward search and backward search, then I can explain you. Let's say here from this IIT Patna I have to go somewhere. For example, let's say some city. Let's assume it's Rajgir. I have to go. I have two options. I can take car or I can take bike. But there is also a constraint that I want to explore the way, right? There could be two possibility. While going from here to Rajgir, I can go on bike, and I can come with, you know, car. This is one option. Another option would be go on car and come on bike. Both way you can explore, right? This is my source and this is the goal. So if I am going from here and then doing exploration to the goal, it is what is happening. It is happening to like a forward search. But backward search means I have reached the goal, and from there I am deciding how I will reach from Rajgir to IIT Patna campus. So there also I explore the path, but it is like a backward search, and this is the difference between forward search and backward search. Another, if you mix these two, it's known as a bi-direction. If I say I don't have much time, so what I'll do, I'll start and my friend also start. I'll do forward search from IIT Patna and let's do, you know, backward search from Rajgir. Then in way we'll meet each other and our time will be saved. Half time will be only, you know, required to do exploration, and he can share the information, I can share the information. Finally we can merge this information as a unified information. So this is how the backward and forward search differs to each other. So idea is that why not to do the two things together? As I said in the example, if I'll do exploration and my friend will also do exploration, and at the end when we'll meet, the time will be less, and finally we'll have idea about the whole path. So here also the same thing comes. Why not we can mix forward search and backward search together, and that's known as a both way search or something. When is the bidirectional search applicable? So this is the bidirectional search. You are searching in the both way. You are doing forward search, you are doing backward search. It is known as a bidirectional search. Is it complete? Given the scenario, given a problem, is it always find solution if it exists? Answer is yes, it will. What is the time complexity? If you see, it become d by 2. Initially it was d, but it become d by 2 because both way exploration is happening, right, in the parallel. So its time complexity is reduced, and so the space as well. So it's becoming d by 2 rather than you have to do d is what? D is your d is what is the depth where you can find the optimal solution. So it's d by 2. Half it becomes. Initially for it used to be O ki power order of B ki power D, but here it becomes D by 2 because we are doing both way search. That's why. Is it optimal? If I'll give you the problem whether it will find a path which cost will be always minimum. Yes, uniform cost search can use in the both direction. If you'll use the searching technique uniform search in the both direction, doing the forward and backward, then finally yes, it can do the give you the optimal solution. Now let's summarize the algorithms that we have discussed till now. So what criterions we had completeness, time, space, and optimality, right? And these are the algorithm: BFS, uniform cost, depth first search, depth limited, iterative deepening, bidirectional, right? So in terms of completeness, if you see, depth DFS is not right, but others other than the depth limited, we have the solution. Yes, we can guarantee if there used to be some solution, given the problem, it will converge there. In terms of time, if you see exponential O of B ki power D and all going there, so for bidirectional it's quite less compared to BFS, which is O ki power B B ki power D. Here is B ki power D by 2, which is becoming half, right? So if I ask which one is taking more time, whether it's DFS or BFS, what would be the answer? Just think for a second and say what would be the answer. Just see, for the time complexity for BFS, it is taking order of B ki power D, and for DFS it is order of B ki power M. Now you say which one is most costlier in terms of time. Which algorithm should I use if I have to prioritize time? Yes, so which one is more costlier? Okay, so let me explain. So if you have to compare these two factors, order of B ki power D and order of B ki power M, base for both is same B. The only difference in exponent part, which is which is D and M. Now which one will be higher? Those algorithm would take more time. So what is D? D is the depth, M is the depth. M is the maximum depth and D is the depth where you can optimally find the solution. So which one would be lesser? D would be lesser than M, right? So beekeeper M would be more than compared to beekeeper D. So which one is taking more time? DFS is taking more time compared to BFS. So this is how you have to do. Which one is optimal? Optimal is uniform cost, and all other have some constraints. So these power, if you see those now, superscripts, there are some conditions which has been explained in the caption given to the figure, so that you have to see. Now coming to the problem. So whatever till we discuss these algorithms, they are all like a blind algorithm. You don't have additional information, you are exploring and then the final solution. These are the kind, Now coming to the solution, can we add some guidance? Guidance means extra information. They are acting as heuristics. Can we put it like that? Can we do uniform search? So this is always better to do uniform search if you'll have some additional information about the problem. But for few scenarios, obviously you need to do ununiform search, because uninformed search, you don't know about the problem, there you have to do. But if you have some idea about the problem, that you can use as the heuristic while expanding the nodes. You can say no, these branch never will go to the solution because it has so and so, if additional information or the domain knowledge if you'll have, right? So those expansion time space would be saved. So that's why we'll doing informed search is more better than uninformed search, and next lecture we'll talk about that. But before that, we'll do some assignment solution for this problem and we'll discuss about that, right? So there are a few MCQ that we'll discuss, and then there are a few numericals that we'll try to solve, and then we'll discuss the next part, which is informed search, where you will have information about components and you have to say do the searching. So extra thing would be, with the extra information you will get some idea whether you should explode some branch or not, right? Like that, you will be given a guidance for those things, so that those things would be there. So now we'll discuss a few problems regarding this topic, and then we'll discuss. Let's discuss. So first problem is, what were the reasons leading the first AI winter in 1974 to 80? So there was a segment 1974 to 80 where first AI winter has been termed. Why it is so? What was the reason? Just think for a second. And the options are failure of machine translation. So machine translation, you must be knowing translating from one language to another language. So from Hindi to English, English to Bengali, Bengali to Tamil, like that. Decline of Lisp. Lisp is the programming language. So decline of the Lisp was the reason for calling AI winter. Poor speech understanding. So model were not able to do the understanding of the speech properly was the reason. Negative results of neural network. Neural network were giving not in favor results. So what were the reasons why first AI winter has been called for 1974 to 80 period? The reason was this: the failure of machine translation, decline of Lisp, no, poor speech understanding, yes, there was, negative results of neural network. So these three options would be correct for calling AI winter in 1974 to 80. Now coming to the next question, which of the following is or are reasons for recent takeoff the deep learning? Why these days deep learning has been it's so popular, although it has been proposed very early, why it has become popular in last 5 years. What is the reason? The options are: it can be used to model real world problems, increase computation power with the advent of GPUs, numerical optimization and algorithm efficiency, and access to lot more level data. So what were the reasons deep learning become, you know, such famous these days? Yeah, so a reason it can be used to model real world problems. It's not like that, because it used to be real world problem could be modeled 20-30 years back as well. Increased computation power with the advent of GPU, that's true. Nowadays you have the computation power, that will be the reason. Numerical optimization algorithm efficiency, it has been increased over years, that's true. Access to lot more level data, now we have so much data, and that too label with some information. Is it so? Yes, these are the three reasons why deep learning has become so popular in last 5 years. Now coming to the next question: which action is the rational agent expected to prioritize? So if a rational agent used to be there, what action it will try to prioritize? So options are the morally correct actions, which are morally correct, actions which leads to the greatest reward, action which leads to less loss, socially acceptable solution. So which one would be correct? It's pretty easy, so you people can guess. Obviously it doesn't know moral. Rational agents, AI agent don't know, so it will not obviously do action that will give the greatest reward. Yeah, that's true, because that's how the objective has been, framed. So it will do the action, it will take the actions which will give it highest reward or the greatest reward. So that's why option B would be correct, action which leads to less loss. That's also some sense true, because action which will give you the less loss it will try to do. But if it has been optimized or framed in terms of reward, then it would be do the greatest socially acceptable. So it has nothing to do with the society and all, right? So even the definition is like that. For each possible percept equation, does whatever action is expected to maximize the performance measure on the basis of evidence perceived so far and built-in knowledge. So this is the definition. Given the information, given the learned behavior, what it will do so that the maximize the performance measure, right? If the performance measure is reward, then it will do the action which will lead to the greatest reward. If I have changed the definition and say it, for each possible percept sequence does whatever the action is expected to minimize, let's say, loss, then which option would be correct? The third one would be correct. Now coming to the next question: what is an expert system in context of AI? So for a context of artificial intelligence, which of the fourth definition become more is appropriate for expert system? The options are: a group of human experts which have high skill with respect to particular field or task; an AI system which consists of encoding knowledge of the entire domain using the logical form using that knowledge being used; an AI system which asks human experts only if it is unsure about the prediction on the task; or none of the above. So out of these four, which one suits most for expert system that you have to answer? Yeah, think for a second and then we'll discuss the answer. Which one is here more appropriate is the second definition: an AI system which consists of encoding knowledge of the entire domain using a logical form and using that knowledge base to reason. So here AI definition is to encode the information what you have and use that information to reason. Reason means given the scenario, if someone will ask what to do, whatever the information you had, you first encode it in logical form and the process that the database, or if I say knowledge base, given the inference constraint and see whether these two contradict each other or satisfy each other. If it satisfies, you can answer accordingly. The system will say yes, it could be possible. If not so, then it can say no, it's not possible in real world because the information it has encoded are contradictory to the inference or the query someone has triggered. Now going next. Strong AI hypothesis says machines should only act intelligently, machines should only think intelligently, machine that think intelligently must act intelligently too, and machine that act intelligently must think intelligently. This is very good question. So think which one would be correct. What is the strong AI hypothesis? Which of the four is the correct one? So thinking and doing, it has been designed like that. Yeah, so which one would be correct here? Whether machine should only act intelligently or think intelligently or both, but if it think intelligently must act intelligently, which one should be correct? Machine that act intelligently must think intelligently too. Yeah, that's here. If you see why so first two options were only, but here the two are like both it can do, but the reason has been different. So the which is more separate is machine that act intelligently must think intelligently too. If it is doing good, it's most likely that it is thinking also intelligently. That's why it is doing that behavior, right? So this was the reason, and this is the most appropriate. Now coming to the next question. Suppose that there are the two nodes u and b in a graph. There is a graph and there are two nodes u and b. We find two paths connecting two nodes using BFS and DFS. So we do the BFS and DFS. The first path is P1, the second path is P2. The P1 is done by BFS and the P2 is done by DFS. Now it's saying what can be said about the length of two paths, this P1 and P2. So path written by BFS will always be shorter than BFS. So this is just a comparison between P and P2, P1 and P2. P1 will be greater than P2, P1 greater than equals to P2, P2 greater than equals to P1, P2 greater than P1. So these are the four possible, and asking which one should do. Both algorithms will always return the same path. This is also option, I missed it. So you need to say which one would do in terms of length of path, whether BFS or DFS given the scenario. So just think about that. Let's say imagine a graph. You have root node R, and there are U and V somewhere. Right. So it is saying there is a path. Which one will take less path? In DFS, what you go do? You do depth, right? In BFS, you do breadth. Now think about it. Yes, so you think if you have could come up with that, that the reason would be path written by BFS, that one would always be longer, path written by would never be longer than the written by DFS. Why it is so? Because in BFS, if you see, you are doing breadth-wise. In DFS, you are going depth-wise. So if you are doing DFS, you are going in depth, right? A, B, D, E, something like that. But U and V are the two edges of the graph. In BFS, we don't know where U and V are because we don't know the position. So what will happen if, let's assume some scenario, U and V would be at in the, let's say, in the same branch, for example. So what will happen if they are in the same branch? For U to be for U to be path would be one only. Find the two parts connecting the two nodes using the BFS and DFS. So for BFS, what it would be, it will go from, in one go it will find out, right? Because they are the node of the same children. But for DFS, what it will go, it will take the first children and it will explode in between them, right? So it has obviously taken more paths than BFS, because finally it is going depth of the children, while in BFS it has nothing to do there. So for this scenario, what will happen, the path written by BFS will no longer be longer than written by the DFS. That is the reason. I just give you the scenario. For other scenario also it holds. Now coming to the next question. Suppose we are playing a game where there is a one goal state and each step has cost in range of 1 to 100. Now we used to find out the optimal path starting from initial state. Which of the search algorithm are guaranteed to be optimal? So that we have to say whether it's a BFS, whether it's a UCS, iterative deepening search, and bidirectional uniform search. What would be there? So here cost is involved, but in other algorithm cost is not uniform other than uniform cost. So if it's just selected, it will be both uniform cost search and uniform cost bidirectional uniform cost search. So this is how it works. Now coming to the next question, what are the following graphs? Search with the full duplicates, duplication Ds. It is just asking the definition of BFS and DFS that you can easily say is so the time complexity for what will be the BFS, and space complexity for DFS it would be O, B keep RM, and order of BM respectively. Now coming to the next question, this is, you need to do it on paper. So A is the initial state, here is the source, I want to go to L. If you do BFS, what will be the path? Just do it. So from A to L we want to go. We start from A and we'll go to L. L is the goal state, and the search algorithm which is given to us is the BFS. And one constraint also, always prefer lexicographical smallest. What does that mean? For A there are two childs, B, C, D, right? So which one should I select? So it is saying select the lexicographically smallest. So you should select B because B comes first and C and D. In that way you just run the BFS and see what is the path is coming. I am giving a minute. Yeah, so let's run the BFS. I think you people have got the solution now. Match with me whatever I'm saying. So we are doing BFS here. So what will happen, we are at the A, we have three options B, C, D, right? So let's also write it somewhere. What to do with the solution for that? So I could have so just match what I'm saying. So we are at the A, we have B, C, D, and as I said, we are doing the lexicographically smallest first. So we'll expand B first. So we expanded B, then C, and then D, right? So we have A, B, C, D. Now for B, you'll expand E and F. For C, you'll expand G, and for D, you'll expand H. The second layer has also done. Now we'll go to the third level, which will be I. For E, you will do I. For F, you will do J because I already has been explored. For G, you will do K, and for H, you will do nothing because K already is explored. So the order is A, B, C, D, E, F, G, H, I, J, K. And for you again go to I and you are doing exploration of L. So finally it will be like that. The order will be simply the order A, B, C, D, E, F, G, H, I, J, K, L, right? So this is how the BFS works. So this must be now clear to you. In a graph where the goal is neither a root nor at the depth one, iterative deepening search will definitely expand how many nodes, more, less, or equal number, or cannot say compared to BFS. So this is the searching algorithm is given. So it's always going to explore more because the situation is given, it is neither the root nor at the depth one. So the difference between what these are two algorithms lies here. If you see iterative deepening search, iterative deepening, so we do 1 and then we double it 2 and then 4 like that. If you have compared to BFS, it is happening breadthwise, right? So this is why solution is here, answer would be more. Now next question, in BFS how many times a node is visited? In BFS algorithm, if you have to run, how many times a single node will be visited, with this once, twice, and equivalent to the number of in degree of the node, and thrice. It's a very tricky one. Just think for a second and then say. Yeah, so if a node will have different in degree, right? From A I'll go to B, C, D, right? So this number of times, because from there also I'll come there, right? So this is how it is. Answer would be equivalent to number of in degree node. Next question. This is the scenario and it is saying apply the BFS, similar to question which we have done. Start is the G. What will happen? G would be start, then what will be the BFS? If you have to do the lexicography again, then you what will do? For G you will expand A, I, or J, right? Because A first, then I, and then J, because lexicographical. So it will be G, A, then I, G, A, sorry, H is also there, or node. So it will be G, A, H, I, J, and it will expand, you will get to the answer, which will be option 3, right? Now coming to the next question, this is interesting. This is the goal state and the source state, right? The 8 puzzle problem. What is the maximum number of state, also called the branching factor, you can have? So how many, you will have maximum subnodes? So because here the blank can move left, right, up and down, but not for this scenario. In general scenario, how many it can have? 4. So 4 would be the answer. Next question, what is the state space size? This is the state and how many states can it have? Each have 9 possible option, 1 to 8, and then blank. Then finally if you do 9 for one, then for other it will be 8, for other 7, and you multiply them, it will be 9 factorial finally, because 9 to 8 into 7 is equivalent to 9 factorial. The next question is consider the running BFS algorithm. Start with S. Okay, so saying you start with the S from source to goal. From this is the source and you have to go to the goal. In how many steps you'll go if you apply the BFS? So we applied, let's say, BFS and see how much it is going. This is the source. If you'll expand it for blank, it will either go to up or right. That we have done. For this one, it can go to where? This one can go to the right or it can go to up. So that's why the 2 options. For this one, again the 2 options. If you see, this is the where we want to go. 1, 2, 3, 4, 5, 6, 7, and 8. This is the goal state. So how many nodes you have visited, including the source? 1, 2, 3, 4, 5 and 6. 6 nodes we visit, then we reach to the goal. So this was the question, how many nodes? The 6 nodes would be there. Okay, so this is how we have done here. So problem, and next class we'll be reading about, you know, the where we have some information in